Okay, afternoon. So we're going to start something completely different today. Well, at least completely different compared with last week. So as I mentioned, I guess at the end yesterday, we're going to start talking about these things called inner products. All right, and so inner products are just the abstract generalization of dot products. So vector spaces with the abstract, the axiomatic vector spaces with the abstract generalization of Rn. Linear transformations with the generalization of matrix transformations. And inner products are generalizations of the dot product. Okay, so what does the dot product do? The dot product takes two vectors in Rn and gives you a number in Rn, okay, a real number. So the inner product on a vector space is going to do the same thing. It's going to be a machine that takes two vectors in your space and gives you a real number. Okay, so it maps a pair of vectors to a single real number. And we're going to have to give these, so it's really a function from v cross v into R. We're going to have to specify some properties that these functions have to obey if we want these functions to behave like the dot product. Right? And if we want this to be some kind of meaningful generalization of the dot product, we have to, I guess, think about what properties of the dot product are actually crucial. So what do we use the dot product for? See if what, sorry?
The alignment between the two vectors.
Yeah, you can measure the alignment between two vectors. And so what does that kind of give you geometrically? What do you? The angle, right? So you can use dot product to measure angle. What else can you use dot product to measure? Length. What else can you use dot product to measure? So orthogonality is related to angle, right? So orthogonality is a special case where the angle is pi on 2. What else can you measure with the dot product? Gives you some kind of notion of distance, right? So using the dot product, if you're in Rn, you can say how far apart these two vectors are. You can say how long this vector is. You can say what the angle between these two vectors is. Okay? So all of these properties are sort of geometric properties of our vectors. So by specifying an inner product on our vector space, we're going to get notions of geometry. Now the first thing to be aware of, and this will come out as we go along, and that's that there's no, you should fix the lighting so you can read these slides better. There's no unique way of specifying an inner product on a vector space. Right? There's no correct inner product on a given vector space. So even on Rn, we're going to generalize the dot product. The dot product is not always the inner product you want to put on Rn. There are loads of applications where the inner product you want to put on Rn that's actually useful for your problem is something different to the different to the dot product. Okay, so there's not going to be a unique correct way of putting an inner product on a vector space. There's just whatever way you think is useful. And what we want to do is specify general properties of any particular inner product you want to put on your space. Okay, now, so all of this block says here is just that the inner product is a map that maps a pair of vectors to a real number. Now it satisfies three properties, okay? And three properties, if you stare at them, are all satisfied by the dot product, which is not surprising, right? Because this thing's supposed to generalize the dot product. So the first one is symmetry. So the inner product of u and v is always the same as the inner product of v and u. If you've got some map from v squared to r that doesn't satisfy that, it's not an inner product. You might still have a well-defined, useful, interesting map, but it's not an inner product. The inner product is linear in its second argument. Okay, so if you hold the first argument fixed, so we're taking here the inner product of u with v plus kw. We're leaving the u completely fixed. The inner product is a linear function of the second argument, right? So the image of the linear combination is a linear combination of the images. Now, if you stick property 1 and 2 together, what do you learn?
The first is also linear.
Yeah, right? So inner products are also immediately, if you stick properties 1 and 2 together, linear in the first argument as well, right? Because you just start off by swapping the two things around, and then the first argument becomes the second argument, and it's linear in the second argument, okay? But you don't need to specify that in the axioms. So we're always trying to make our list of axioms as small as possible. A, because that looks better, and B, because when you go and prove something, some specific example you're interested in is an inner product, you've got a shorter list of rules to check. Okay? So it is linear in the first and second arguments, but you don't need to specify that in your list of axioms. And then the third property is, I guess, the most subtle of them all, but it's also crucial. And if you didn't have this property, you wouldn't be able to meaningfully define things like length and distance, etc. And that's this idea of positive definiteness. There's two pieces to positive definiteness. The first is pretty easy to understand. It's just saying that if you take the inner product of V with itself, it's always non-negative. Right? So for any V, this is a for all V statement, right? This was for all vectors. So this is a for all V statement. The inner product of V with itself is non-negative. Now, what's also true, and is crucial, and is the thing that people often sort of gloss over, but it's crucial, the only time you can get equality here is when V is 0. Right? The inner product of V with itself is only 0 if V is the 0 vector. Right? There are no other vectors sitting in your vector space that have inner product with themselves equal to 0. So this is, in particular, if you stare at this is really saying your inner product knows quite a bit about the structure of your vector space. Right? It knows what the 0 vector is. It knows it's only allowed to say the inner product of some vector in itself is 0 if it's the 0 vector. Okay. And actually, just one comment about the use of scalars. Right? So at the end of chapter 4, I said that everything we'd done in chapter 4 worked if you replaced the reals with any field you liked. Right? That was true. In fact, everything we did in chapter 5 also holds if you replace the reals with any field you like. Defining inner products is different. It's pretty easy to make maps that satisfy those two things over any field, and this is sort of useful. But this last property of positive definiteness, this is really crucial, and this is really, you can do it over the reals, you generally can't do it over arbitrary fields. Okay? You can also do it over the complex numbers if you define things the right way. But here so everything that I'm going to say in this chapter is really just for reals. Okay? The scalars have to be reals now. There is a version of this that works for complex numbers, but then you don't actually want this. You have to replace that with something a little bit more interesting, which we'll talk about in 2025. Okay, but this chapter, chapter 7, the scalars are reals. Okay. So if you've got a vector space and you define an inner product on it, you now have an inner product space. And again, just to emphasize, if I just give you a vector space, there's, in general, infinitely many inner product spaces associated with that vector space. Right? The vector space doesn't have an inner product coming with it. There's always infinitely many different inner products you could put on that space. You pick one that you think is useful, and then you've got an inner product space. Okay, so first little lemma, we've already stated, you put axioms 1 and 2 together, you find that the inner product is linear in the first argument. And obviously, the dot product satisfies these three properties, right? The dot product is an example of an inner product. You don't even need to go back and prove that because we proved that in chapter 1, or 3, actually, chapter 3. All right, so the dot product is definitely an inner product, but there are loads of other useful examples, and even in Rn, there are loads of other useful examples. All right, so let's do a poll. So, is that true or is that false? If the inner product between two things is 0, then one of them's got to be 0. All right, true or false? If the inner product of u and v is 0, then you've got to have at least one of u and v being 0. All right, so if you think it's true, you should be able to prove it from the axioms. If you think it's false, you should be able to write down a counterexample. Okay, anybody want to offer an opinion?
False, I think it's false.
False? What do you reckon it's false?
Just if we use the example of the u is equal to negative 1, 1 and v is 1, 1, we get 0.
Yep. So if you take u equals 1, negative 1, and v is, what'd you say, 1, 1, there in R2, right? So, and I guess you're using the dot product.
Yeah, it's just the easy example.
Yep. So there's an example, right? Then u dot v is 0. So this is false for the dot product in 2 dimensions, so it's going to be false in general, right? That's a counterexample. And you could also just pick E1 and E2 if you liked in R2, right? So this is really saying something that you should be familiar with. This would be claiming that the only time two vectors can be orthogonal, that's what having inner product 0 means for the dot product. It would be saying that the only time you could have two vectors being orthogonal is when at least one of them is 0, and we know that's false. So those need to be pointing in perpendicular directions. Okay. Now, so what's an example of something on Rn that's an inner product that's not the dot product? So here's one generalization of the dot product on Rn, okay? So it looks like the dot product, right? So this, if I didn't have these w's here, this really would be the dot product of u and v. But if I stick in any collection of strictly positive weights, right? So each of these wi's I can consider as being a weight, I still have an inner product. So the idea here is that you're sort of saying certain directions in coordinate space are more important than others, right? If you think one direction is really important, you can give it a big W, and then it'll contribute more to the inner product. And one reason you might want to do that, we'll touch on later, is if the Rn that you're considering is really the space where some big data set you're interested in lives in, then the statistics of your big data set will dictate what directions in this enormous space are more important than others, right? And then there'll be a corresponding inner product associated with that. And so there's really practical reasons in data science, machine learning, statistics, et cetera, for looking at inner products other than the dot product, even if you're in Rn. All right, so let's show that this thing with these weights is actually an inner product. So what do we have to do? We've got to show that it satisfies our 3 axioms of an inner product. let's say we've got u and v and x, and they're all in Rn, and we've got some scalar k. So the first property is symmetry. So we want to consider the inner product of u and v. That's the inner product of u and v. Now, each term here is just a product of three real numbers. If I take u1 multiplied by v1, that's the same as if I take v1 and multiply it by u1. So you can swap the order of all of the u's and the v's. And then you stare at that, and what have you got? You've got precisely the inner product of v and u. So this symmetry axiom holds. Okay, now it's not a very complicated argument. It holds just because real numbers commute. Symmetry is not usually very tricky to verify for whatever example you're interested in. So now let's think about linearity. And our axiom just says you only need to check it in the second argument. So let's look at what the inner product of, so we'll keep u fixed, and we'll look at the inner product of u with this linear combination, v plus kx. So just do it by definition. So it's w1 times the first entry of the first argument times the first entry of the second argument. First entry of the second argument is v1 plus kx1. And then you've got the same thing for the second entries, yada, 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 up to the nth. Same thing for the nth entries. So you've got un times vn plus kxn. Okay, that makes sense? Now, I'm back to having just a statement about real numbers. So we can use properties of real numbers. So w1, u1 is just some real number. v1 and kx1 are just some real numbers, so I can expand all of this out. All right, using distributivity and associativity and commutativity of real multiplication. I get that. That's expanding out the first term. Do an analogous thing, expanding out the second term. Now, what do I want to do now? What should I do next?
Rearrange it in order to have the k terms together and then the other without the k.
That's right. So the k terms have got the u's and the x's in them, and the non-k terms have the u's and the v's in them. And remember, I'm trying to show that this is equal to the inner product of u and v plus k times the inner product of u and x. So I want to grab all the pieces that don't depend on k. And then the piece that does depend on k. Okay, that's just collecting all of the terms together that have a k and don't have a k, factoring out the k. And I can do that because, again, all these things are just real numbers, so we can change the order we add them and multiply them, and we can pull out constant factors, etc. Now this is precisely what? Yep. This is the inner product of u and v. And likewise, this is k times the inner product of u and x. Okay? so linearity holds. All right, because for each fixed u, the inner product of u and whatever is a linear function of whatever. Okay? It preserves linear combinations in the second argument. So, is everybody happy so far? All right, so what about positive definiteness? So now we just need to consider inner product of v with v. And we're going to do two things. So let's write it out. So this is v1, w1 v1 squared plus blah, 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 plus wn vn squared. Agreed? Now, all the wi's are non-negative. In fact, they're strictly positive. And since we're working in Rn, all of these squareds here are non-negative. You can see this wouldn't work if we were working in the complex numbers, because then we'd have squares of complex numbers and they wouldn't be non-negative. But if we're working over the reals, all these squares have to be non-negative. So we've got a sum of non-negative terms. So each of those so that sum is non-negative, so that part's easy. But why is it obviously the case that this thing only vanishes when all the v's are 0?
If there is one larger than 0, then the whole thing will be larger than 0. Because the others will, the minimum will be 0. And you plus 1, and then it will be large.
So this is telling me the minimum 0, but I guess there's a unique thing there's a unique minimizer. There's a unique point that minimizes this thing. And it's going to hold because if any of these VI's were non-zero, their squares would be strictly positive, right? And then our assumption that the WI's are all strictly positive comes into play, right? Then you would have a term that was strictly positive. And then you've got a term that's strictly positive plus a bunch of stuff that's non-negative. There's no way you can get cancellations. So your answer is strictly positive. But this only works because those W's were all strictly positive. If some of the W's could be 0, this doesn't work and you don't have an inner product. Okay? The W's, these weights, have to be strictly positive. So let's write that down. So if this thing does happen to be 0, then what's actually going on? Well, we've got a sum of non-negative terms. The only way that a sum of non-negative terms can be 0 is if every single term vanishes, right? Because you can't have cancellation because everybody's non-negative. So the only way that this thing could possibly be 0 is if every single term individually vanishes. The W's themselves don't vanish, so it's got to be the VI squareds that vanish. All right? And the only thing that squares to 0 is 0. That holds for a y, so v is the 0 vector. So positive definiteness holds. All right? But it's crucial that we prove both of these things. This is not enough to prove positive definiteness, right? That's just sort of the first really easy part of proving positive definiteness. What you need to show is that the only time this holds is when this holds, right? That's really the crux. And that's the part that usually requires a little bit of thinking if you're trying to show that something is an inner product. But it's also the crucial part of being an inner product because this is what lets us define lengths and distances, etc. Okay. So, is everybody happy? Yep.
Because we said that use I is any positive real number. That means strictly positive, right? Because it can't be zero. Zero is not a positive number.
So we're talking about the W's?
Yeah.
Yeah.
Because if it's
So it can't be zero. Strictly positive means, well, positive means non-zero.
okay, yeah.
So I guess, yeah, that is partly a question of convention. In the olden days, sometimes I think positive included being zero, but that's why I use the word non-negative. So non-negative means you can include zero. Positive means you don't include zero.
Okay, just making sure.
Yeah. So, and when I say positive, I mean strictly positive. I'm just saying strictly to emphasize that it's positive, right? And positive and strictly positive are the same thing. Just a question of emphasis. All right. So what's another example in Rn? So here's basically the most general thing that you can cook up in Rn that works. If you have an invertible n by n matrix and you map U and V to this crazy looking matrix product, U transpose AV, and you do that for every U and V, then you also have an inner product. And you basically can't do anything more general than that. But this is interesting because what this is saying is that in Rn, every single choice of an invertible matrix gives you an inner product. Okay? So there's not one inner product that makes sense to put on Rn. There's infinitely many. And any choice of nice invertible matrix you find it interesting gives you an inner product. And this is basically where it comes from in statistics, because then this matrix here would be like the matrix full of your data, etc. Something like that. Okay? Some kind of sample matrix or something or other. Now, if you were going to try and prove this, I'll leave this for the problem set, but if you were going to try and prove this, how would you go about it? I mean, you have to prove those three axioms. What sort of jumps out at you about the structure of this thing? It's not completely random. It's not just, it looks like the product of four things and there's some transposes and wires that look like that. But if you stare at it, there's a bit of structure here. So what does it really say?
With the UV transpose, just with the UV, just with the phi, you just be a transpose of that.
Yep, so U transpose A transpose is really just AU transpose. Right? So you could write it like this. And then what's that starting to look more like?
Like a dot product. If the U and V are the one column matrix, then it will look like a vector dot product.
That's right. It's really just the dot product of AU and AV. So what we're really doing is just transforming our vectors first by hitting them with A, and then taking the dot product. So in a sense, I mean, it is a different product of the dot product, but you can define this thing using the dot product if you like. And this might be an easier way of proving that it satisfies all the inner product axioms, because you can use certain properties of the dot product. So for instance, symmetry, linearity are going to be easy, not completely immediate, but easy, because you know what holds for the dot product. And you'll need to think about positive definiteness. And think about, when you're thinking about positive definiteness, why do you think we actually need A to be invertible? Because if A is not invertible, this doesn't work. You don't have an inner product. So when you're thinking about how to prove positive definiteness, make sure you're thinking to yourself, why do we actually need invertibility? Okay? All right. Is there any questions about that example? Nope. All right. So here's an example that maybe superficially looks completely different, although in some sense it's some real sense. It's actually just the natural generalization of the dot product to a space of functions. So if you've got any two, say, nice enough functions that you know how to integrate them, you know how to integrate their products, so let's say you've got continuous functions on some interval, then you can define the inner product of those two functions. So you can define an inner product on this space, right? So this is the space of all vector space of all continuous functions on the interval AB. So we can put an inner product on this vector space, and we can do it by saying the inner product of two of these functions is just the integral of their product, right? And this really is just like the dot product, because what's a function? It's really just like a vector, except that the entries aren't being indexed by the numbers 1 to n, they're being indexed by, you know, an entire interval in the real line. And so what are you doing here when you do this integral? You're just adding up the products of all the entries, right? Because an integral is just like a sum. And so this is really just a natural generalization of the dot product, and there's sort of two examples of the same thing. And if you go on and do stuff in maths that involves analysis at any level, you'll play with this thing a lot. Okay? This is the sort of standard canonical inner product that you would put on a function space. And you can prove that this thing satisfies all of the axioms, so it is actually an inner product, and you can do that on the problem set. But exactly the same steps that we did in the previous example, but you just have to translate it to this setting. So that's just a comment that this thing looks like a dot product. And in the same way that we generalized the dot product by including positive weights in front of all of the entries in the sum, defining the dot product, you can do the same thing for this integral inner product. Okay? So you can take any strictly positive weight function you like, and you can shove that into the integral, and you've still got an inner product. And in fact, there's an even more general version of it that I don't think we'll talk about, where if you know how to generalize this sort of thing to functions, and I won't talk about how you might do that, but you can, then there's a version of this for functions as well. But certainly this thing where you've got any strictly positive W, that gives you an inner product, and you can check that this thing satisfies the inner product axioms, and it's just the analog on continuous functions of the weighted inner product that we proved was an inner product. Okay. All right, everybody still with me? Questions? All right. So here's, I guess, something that's not that surprising. It basically just follows from axiom 2, but it's worth being really conscious of. So there are things called linear functionals, which the 2025 people have already seen. But a linear functional is just a linear transformation that takes its values in the reals. Okay? And one way of interpreting what axiom 2 of the inner product list of axioms says is that for any fixed choice of the first argument, you have a linear functional. Okay? It's a linear functional of the second argument. So we can prove that immediately. Really doesn't require anything except the second axiom. So how do you prove linearity? You take two vectors and a scalar, make the simplest possible linear combination, which is a scalar multiple of one of them added to the other, and you try and show that your map preserves that linear combination. Then you've got linearity. So what's the inner product? Sorry, what's T of W plus KV? Well, and actually I'm fixing the second argument here, but by symmetry it doesn't matter, but let's say we're fixing the second one. So I'll actually need two axioms. I'll need axiom 1 as well. So that's the definition of T. from our lemma, we know we're also linear in the first argument. That's sticking axioms 1 and 2 together. So this is T of W plus K times T of V. All right, so T is linear. So there is a relationship between certain linear maps and these inner products, right? As soon as you fix one argument, you've got a linear function out. Yep?
Why is it T of V, not T of X?
T of V, not V, blah, 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 because I did it wrong. Thank you. So it should be, hang on. No, I haven't done it wrong. Have I have written something wrong. Yes, that's that. So X is the, hang on, V is the fixed thing. Yeah, what have I done? That should be X. That's what that is. That's what we've got, and now it makes sense. Yes, I think that looks right now. Okay? All right. So one natural question is, do all linear functionals look like that? And the answer is yes. And we'll talk about that in 2025. But that's not as obvious, but in fact, every linear transformation taking values of the reals, you can interpret as being an inner product with one of the arguments fixed. There's this nice relationship between these linear functionals and inner products, and that relationship actually is important in quantum mechanics, which you may or may not want to appreciate one day if you take a higher level course in quantum mechanics. Okay, but it's worth keeping in the back of your mind. Okay, so let's do a poll. So does this thing define an inner product on R3? Yes or no? Have a look at it, see whether you think it satisfies the 3 axioms. Okay. If you think it does, just prove that it does. If you think it doesn't, write down a reason why it doesn't, right? Which axiom or axioms does it not satisfy? Okay. So if you stare at it, I guess the first question, if you don't want to just jump in and use your gut, is let's go through all of the axioms. So does it satisfy axiom 1? Yes, right? Because just like in the proof that we had before, I can just swap the terms and all of the, swap the factors and all of the terms over on the right-hand side. So this is inner product of V and U. Okay, so it's certainly symmetric. It's certainly also linear if you go and check it. So the real question is it positive definite? So it looks like you all, or almost all of you, think it's not positive definite. So how do we tell that this thing's not positive definite? Yeah, so what's a counterexample?
If you have, I'm going to say something like U1 is equal to 2, V1 is equal to -1, and then U3 and V3 is equal to 1.
That was in too much of a random order for me. What's U?
U1 is 2, U2 literally doesn't matter, and U3 U1.
Okay. And V is?
V1 you have -1.
-1.
And then V2 doesn't matter, V3 1.
1, yep. Hang on. How is that going to work? Sorry. So, all right, so let's go. Okay. So, all right, let's think about it systematically. So if we're trying to prove positive definiteness, we only actually need to consider one vector, right? Because we're interested in the question, is that thing always non-negative? And if so, does it only vanish when u 0? That's what we're interested in. So what's this going to look like? It's going to look like 2u1 squared plus 4u3 squared. Okay? So again, 2 and 4 are positive and squares are non-negative, so it's definitely non-negative. So it satisfies the first part. But then, I guess if you stare at this, you might be worried that there are some vectors for which this thing's going to vanish, which aren't the 0 vector. So can we think of an example of one?
0, 1, 0.
Yeah, 0, 1, 0 is a perfectly good example, right? And in fact, as long as you pick u1 and u3 to be 0, it doesn't matter what you pick u2 to be. So e.g., if u is 0, 1, 0, then we still have uu equal to 0, but u is not 0. Okay? And you can pick anything non-zero for the second entry of u and you get the same problem. And it's sort of not surprising because, you know, this thing doesn't know anything about u2, so it already looks a bit fishy. Okay. Is everybody happy? All right, so I guess a natural question is, what's the point? Right? What is the point of all of this inner product stuff? And the point is that it lets us define lengths, and it lets us define distances, and it lets us define angles, right? That is the point. If you didn't have corresponding definitions of length and distance, etc., the inner product really wouldn't be worth very much at all. All right, so how do you define length once you've been given the inner product? And the answer is you do it in exactly the way that we did with the dot product. Okay? So the definitions of length and distance, etc., don't actually change because the inner product has enough properties similar to the dot product that you can just use exactly the same relationship between length and inner product, distance and inner product that we did when we were playing with the dot product. Okay? So the length of some vector, so we've got this completely abstract space V, it doesn't have to have anything to do with Rn. This completely abstract space V, we've defined some inner product on it. The length of our vector now is defined to be the square root of the inner product of that vector with itself, just the way that we do in Rn with the dot product. Okay? So that is the length. Now, how did we define distance once we were given length in Rn, or in Euclidean space? How do we define distance? Anybody? Sorry? Yeah. So we defined, in Euclidean space, we defined the distance between two vectors to be the length of their difference, right? If you're in and this works in any vector space because you got any two vectors in a vector space, you know how to compute the difference because vector spaces are closed, right? So I know how to take one, I know how to find the additive inverse or the negative of another one because of axiom 5. I know how to add them together and they'll stay in our space because of axiom 1. And now that I've got a notion of length, I can take the length of that difference. And that's what we define the distance of two vectors to be. All right? So inner product gives you length, and length gives you distance. All right? Inner product gives you length, and length gives you distance. So the distance between two vectors is just the length of their difference. The length of a vector is just the square root of its inner product with itself. And you can write the distance in a more explicit way in terms of the inner product just by using the definition of your length, but it's conceptually easier to just remember that the distance is just the length of the difference, okay? Which makes sense. Now, in terms of fancy language so that you can sound clever, we can call the length the norm for no apparent reason other than that it sounds fancy. And we can call distance a metric, again, for no other reason than it sounds fancy. But they're two words that you'll probably come across if you take any higher level analysis, and so that's all they mean, right? A metric is just a distance function. Norm is just a length function. Now, I guess the only thing to be aware of is that not every sensible length comes from an inner product. Not every sensible distance comes from a length or a norm. But as soon as you have an inner product, you immediately get a length and a distance. Okay? I'm not going to go into the abstract definition of what a length and a distance actually mean, but as soon as you've got an inner product, you can define length like this, and you can define distance like that. Now, once you've been given these definitions, you can consider suitable properties of these things. So the length always satisfies the following three properties. So the first one is another version of positive definiteness. So the length is also positive definite, right? So the length of any vector is non-negative, and it's 0 only for the 0 vector, right? And so this is why we really demand positive definiteness for the inner product, because now we have it for length, right? And you really want it for length. You don't want some vectors in your space to have length 0 unless they're the 0 vector. That would be stupid, right? And positive definiteness of the inner product prevents that, okay? And scalars you can just drag out. That's homogeneity. That follows from linearity. And you get this thing called the triangle inequality. Which is crucial. And in fact, these three properties are the abstract definition of a norm. So any map from your vector space to the reals that satisfies that collection of properties is a norm. And certainly the square root of the inner product with itself satisfies those. And there's corresponding properties for the distance as well, okay? So the distance is symmetric, that makes sense. The distance is positive definite, that makes sense. Right? Two vectors shouldn't have distance 0 from each other unless they're the same vector. That would also be stupid. And the distance satisfies the triangle inequality as well. Okay, so you can prove all of those on the problem set, and I strongly encourage you to, right? Just using the definitions and the axioms of an inner product. Okay, so let's look at an example. Suppose that we've got this inner product on R2 given by this. It's one of these weighted inner products on R2. And let's take two vectors in our space, okay? U and V. Whoops, come back. And we then want to find the length of U and the distance between U and V using this inner product and compare them with what we get if we use the dot product. So the length of U is the inner product of U with itself. So that's 2 U1 squared plus 5 U2 squared. And that happens to be 22. Whereas the Euclidean length would be square root of U dot U, and that happens to be root 5. Right? So they're different. So lengths are not intrinsic properties of vectors. in vector spaces. They're intrinsic properties of vectors in inner product spaces. So the length depends on how you've defined your inner product. So the distance in this inner product space is the length of the difference between this u and this v, and that's square root 7. Whereas if you did it in Euclidean space, you'd get root 2. Okay? So the lengths and the distances depend on how you choose your inner product. They're not properties of vectors just from the vector space. Now there's one final example I'd like to consider, and that's that you can talk about the length of a function. And it may seem like a strange thing, but it's actually a really important thing to do. So if we want to talk about the length of sine, we can now meaningfully talk about the length of sine. What's the length of sine? You just plug in sine into both arguments of our inner product. That's an integral. You compute that integral. If you remember some calculus, you get pi. And what that means is that according to this inner product, the length of sine is root pi. Now that might seem like a strange answer. It's actually a pretty sensible answer.